Swayam Prabha. Digital India. Educated India.
Welcome to today's class of nonlinear vibration. I am Professor Santosh Kumar Dwivedi from Mechanical Engineering Department, Indian Institute of Technology or IIT Guwahati. I taught this course several times and already I have developed this NPTEL course on nonlinear vibration, both web course and video course, and I welcome you to attend this MOOCs course on nonlinear vibration. So, this course is intended for senior undergraduate students, postgraduate students, PhD students and professional from industry also. Particularly the students from mechanical engineering, civil engineering, aerospace engineering, electrical and electronics engineering interested in the study of dynamics and vibrations are welcome to attend this course. So, many industry also will be benefited from the study of this nonlinear vibration. So, particularly this manufacturing industry, automobile industry, aerospace will require nonlinear vibration analysis to improve their productivity. So, the professionals from this industry are welcome to participate in this course. For example, in case of this manufacturing, the chattering in the turning operation is a common phenomena. So, also in the case of other manufacturing like this milling, shaping and other manufacturing processes. So, many times we observe the vibration in the system. So, to mitigate or to observe or to reduce the vibration, so this course will be useful. So, initially you should know how to recognize this vibration, and then after knowing to recognize this vibration, then the study how to mitigate or how to control those vibrations things will come into picture. So, we are going to study a detailed analysis on this nonlinear vibration in this course. So, the course content, will be covered in 10 to 12 classes. So, there will be 9 modules, last modules is on this application and the first module is on the nonlinear introduction. So, which I am going to cover in the first 3 classes. So, the introduction to nonlinear mechanical systems particularly I will tell in the first 3 classes. So, it will be in this first week. So, in the first lecture we are going to discuss regarding the introduction to mechanical systems, and particularly I will tell you the vibration of the linear system and nonlinear systems. So, I will take the examples of single degree of freedom system and 2 degrees of freedom system, and we will see how the analysis of a single degree of freedom system in a linear case and a nonlinear case are different. So, in the next class we are going to study regarding the equilibrium points. So, what you mean by this fixed point and how the response of a nonlinear system will behave. So, those things we are going to study particularly on the fixed point response in the second class. So, then we will study about the potential function. So, then how the potential energy term is related to the equilibrium points, that thing we will study. Then time response, phase portrait, using this time response and phase portrait we will study how to analyze a system, particularly how we will characterize a linear system, how a nonlinear systems. So, that thing we are going to study in the second class. In the third class we are going to study about the simulation of phase portraits from potential function, and we will study or we will know regarding many functions, so which are related to nonlinear vibration. So, here also I will tell you about the superposition rule. So, which differentiate between the linear system and nonlinear systems, and also we will study different type of nonlinear commonly used nonlinear systems or nonlinear equations. For example, this Doping equation, Van der Pol equation, Matthew equation, Matthew-Hill equations, Lorentz equation. So, many other equations which are commonly used in the nonlinear cases we are going to introduce in these past 3 classes. So, in the second week we will be devote for the development of nonlinear equation of motion. So, how to derive the equation of motion using different approach will be told briefly. So, as this is only a 10 weeks course, so or 30 lectures will be delivered, 30 to 35 lectures will be delivered in this course. So, briefly we are going to study how the equation motions will be derived. So, initially I will tell regarding the force and moments based approach, then we will see the energy based approach where I will tell regarding this Lagrange principle and then this extended Hamilton principle, and we will solve some problems or we will derive some equation of motion using this Lagrange principle and extended Hamilton principle. So, we will take starting with a simple spring mass system and this simple pendulum system. We will take off many different continuous systems also to derive this equation of motion. So, then how to solve these. So, after getting these equations, so we will see how we are going to order these nonlinear equation. So, after getting the order of these nonlinear equations, so we will solve them these nonlinear equations by different methods. So, we will take several class actually to solve these nonlinear equations. So, particularly we may take around 9 class to solve or 6 class to solve these nonlinear equation motions. So, initially we will use this numerical solution method. So, directly how by using this Runge-Kutta method. So, to derive or to find the solution of the equations we will first see, then we will use some other methods like this harmonic balance method, Lindstedt-Poincare method, method of averaging, method of multiple scales, and many recent advanced methods which are coming up nowadays. So, or in last decade what are the new methods have been there. So, we are going to study all these things. So, we will devote 6 class to study the solution of this nonlinear equation motion. So, then we will study the vibration analysis of the single degree of freedom system, particularly this Doping equation will be taken and we will try to solve this Doping equation using different methods. So, in Doping equation initially we will take that of a free vibration system, then we can take the force vibration system in which 2 different type of force vibration things we are going to take. So, one is weak nonlinearity and or weak nonlinearity and weak forcing, and second one the hard nonlinearity or the hard forcing term, hard excitation term. So, by taking this hard excitation term, so in module 4, so we are going to solve many problems. So, in hard excitation particularly if the order of the excitation is that of the order of the linear term, then it is known as hard excitation. So, we will devote 3 classes to solve this hard excitation. So, particularly we will see the superharmonic and subharmonic resonance conditions and bifurcations and stability analysis and bifurcations of all these things we are going to study. Then in module 6 we are going to study regarding the vibration analysis of parametrically excited system. So, before that the systems what we have studied, those are forced vibration system, that is when the external excitation frequency is nearly the natural frequency of the system, resonance occur. But in case of a parametrically excited system, so if the external frequency is twice the natural frequency or combination of the natural frequency, then only resonance will occur. So, we are going to study regarding the principal parametric resonance condition or combination parametric resonance conditions in this module. So, we will start with what is known as parametric instability region, then we will apply the flow quid theory and different perturbation methods to solve the parametrically excited system. Then, so till this thing we are going to study regarding the fixed point response, particularly we will be interested to know the fixed point response up to module 6. In module 7 we will see other different type of solutions. For example, the solutions may be periodic, it may be quasi periodic, or it may be chaotic response also. So, these periodic, quasi periodic and chaotic response we will study in module 7, and we will study their bifurcations also. So, bifurcation of periodic response. So, I will study in the first class of module 7, then we will study regarding the quasi periodic response and the chaotic response. So, when the response is called to be periodic, so that thing we will study know in this case. So, particularly if the response can be written as a time varying term where the periods, so it has same response at a particular interval of time, then it is periodic. So, it may be single frequency or it may be multi frequency. So, in case of the periodic response, but in quasi periodic response the frequencies, there is relation between the frequencies, particularly if the frequency ratios are in the, so in case of the quasi periodic system the frequency ratios are commensurable, that means in the form of, so root 2, root 3, if that ratio are in the irrational number, that is root 2, root 3, root 5. So, then we can have this quasi periodic type of response. For example, you may be knowing the beating phenomena. So, the beating phenomena can be represented by a quasi periodic response. Similarly, we can study the chaotic response also. So, in chaotic response, which is a deterministic response, so we will study different methods or different types of chaotic response. For example, this period doubling root 2 chaos, quasi periodic root 2 chaos, or torus breakdown root 2 chaos, and then crisis and intermittency. So, all those things we are going to study in this chapter or in this module of module related to this periodic, quasi periodic and chaotic response. So, then we are going to study several numerical methods for the nonlinear system. So, how to solve a set of equations. So, particularly when our degrees of freedom will be large, then no longer by a single equation we can write the equation motion. So, that time a number of equations will be required to write the equation of motion, and in such cases we should know several nonlinear methods or numerical methods to solve these nonlinear systems. So, particularly we will be interested to know how to solve a set of nonlinear equation, then what are the numerical methods to solve this ordinary differential equations, numerical solution for the ordinary differential equation, and sometimes we may have the delayed differential equations also. So, we will study regarding this ordinary differential equation and delayed differential equation. Then we will study regarding the Poincare section, then this FFT and Lyapunov exponents to characterize the periodic, quasi periodic and chaotic responses. So, we will learn how to differentiate different type of responses based on Poincare section. So, based on this Lyapunov exponent and by the FFT or by plotting the time and frequency responses of the system. Particularly, we will be interested in the previous modules regarding the fixed point response, and there we can plot the frequency response of the system or the force response of the system. So, in last module, that is module 9, so we will be interested to see different applications of this nonlinear vibration course. So, we will take 3 physical examples and we will start with the development of equation of motion to see how to solve those equations and also how to analyze those results, and we will do the discussion on all those things. So, the first system we are going to study will be on the vibration observer. The second system we will be studying on a nonlinear energy harvester, and the third system some electromechanical system. So, we are going to study where the applications may be related to parametrically excited system. So, in this course, so the software also hands on practice session on the software also will be given, and assignments will be given to solve these problems using software like MATLAB or open source software. So, you must learn all these open source software or MATLAB software to solve these problems. So, we will cover all these things mostly in 12 weeks, and so you will get lot of applications and assignments, and you have to do the self study. So, the journals and books also will be referred, and by using those things slowly you will learn. So, how to solve all these methods, particularly we will be using the book by Nafe and Mook, Nonlinear Oscillation by Nafe and Mook, and another book by Nafe and Balchandran also we are going to study. So, next class I will tell you regarding the books and the journals available in this field. So, today let us see, so or start with some applications of vibration, and let us see some applications of vibration and how this vibration, whether this vibration is useful or not useful, and how we are going to analyze the system when the equations are linear. So, initially we will start with a linear system, then later we will go for the nonlinear system. So, many household applications you can find vibration is there. For example, you just take the hair dryer, or the you just take pump, or this compressor, sprinkler, micro oven, or there are several precision or this instrument. So, for example, all these musical instruments you just see, so where you can have the vibration and noise are coming into picture. So, in some cases the vibration may not be useful, and in some cases the vibration is very much useful. For example, in case of the musical instrument, the vibration of the string or the membrane is giving the pleasant notes, and everyone enjoy those vibration musical notes. So, many cases this vibration will be very much useful, and many cases the vibration may not be useful. For example, if there is lot of vibration in the pump, so we may think that there is some failure in the bearing. So, that time the bearing has to be changed. So, similarly, if there is some misalignment in the bearing, or there is some bending in the shaft, or some this gear failure, so many other things may happen which may lead to the vibration of the system. So, by knowing the vibration signature of different instruments, we can tell the condition of the system. So, the condition monitoring of any systems can be done by taking the vibration signature of those instruments. So, let us see some other instruments also. For example, this automobile car engine. So, sometimes you might have heard lot of vibration in the car. So, due to many malfunctionings of different parts of the engine, or the transmission system, or the other systems used in the this automobile. So, by knowing their vibration, so you can easily distinguish which part has to be repaired, and also the ground ondulation in the ground sometimes is transmitted to the vehicle. So, you have to make your suspension system in such way that these ground vibrations will not transmit to the driver. So, while designing this automobile, so all this vibration aspect has been taken care, and due to wear and tear in the tire or in different parts of the automobile, sometimes this vibration will be severe. So, that time, so your analysis no longer be in linear range, no longer be valid, and you must have to go for the analysis by taking the system to be nonlinear. Similarly, you can take the example of a CD-ROM, hard disk drive. So, these are the common things what you have seen. So, where you can always see the vibration in the system. You just take the example of the building, bridge. So, these are the civil structure. So, building subjected to earthquake excitation, high rise building subjected to wind loading also. Similarly, this bridge oscillation. So, on the bridge when the vehicle is moving, so due to this moving load you can get the vibration. Similarly, so if it is a cable stayed bridge like this, the bridge shown here, this is a cable stayed bridge. So, in this case the vibration of the cable, so when the vehicle are moving on the bridge, so you may get vibration in the cable or you may get the vibration of the bridge. Similarly, you may have many other structure, so where this vibration are predominant. So, sometimes this wind vibration and the vibration due to this earthquake are not measured in a quantifiable manner. So, these are not a deterministic forces applied to the system. Many times the forces may be deterministic or without or within a range. So, that time your force are deterministic or the application of excitation is deterministic when you know the particular amplitude and frequency of the excitation, but the excitation in case of the earthquake or this wind loading, so which are varying with time, so may not be known a priori. So, in that case it may be stochastic or probabilistic or the random type of vibration. So, the system may be subjected to different type of loading. So, we will see what are the types of loading we generally consider in our case or in case of vibration. Those things will study slowly, and so some other examples also you can see in the slide. For example, this human motion. So, when is moving, so the motion of the human may cause the vibration also. So, particularly when they are moving in a group on the bridge. So, you can find the due to the rhythmic motion of the persons, so the force will be transmitted to the bridge. So, here some examples actually given for the energy harvesting by using the shoes during this human motion. So, if we are putting some piezoelectric patch, so in the shoe, so then the motion can be converted. So, the motion of the human being can be converted to electrical energy by using this piezoelectric patch. Similarly, in the bridge or the building we can put the piezoelectric patches to convert actually the vibration energy into electrical energy. Similarly, many other places we can use these piezoelectric patches or other different type of energy harvesting systems to generate energy. So, here in this slide several examples are given. So, when we will study the last module, so that time we will study more regarding this energy harvesting system. So, here also one more energy harvesting example is given. So, galloping based energy harvesting, that is piezoelectric energy harvester. So, here this is a bluff body. So, this bluff body, for example, if it is placed in front of the UPS, so due to the small wind coming out of the UPS, it get vibrated, and that vibration energy by putting a piezoelectric patch. So, here we have put a piezoelectric patch. By putting this piezoelectric patch, you can see the voltage generated in the oscilloscope. So, the voltage generated in the piezoelectric patch can be seen by using the oscilloscope. So, you can generate a voltage of few milliwatt and in the order of several volt also by using this type of energy harvester. So, you may have a vibration based energy harvester or this wind based energy harvester, and there are several other way of generating this energy. So, those things we will study in the last module of this course. So, let us see. So, what is a vibrating system, as we are going to study this vibration. So, this shows a simple pendulum, so which has been given so initial disturbance. So, now it has been given some initial disturbance, it has been taken to this place and it is released. So, if it is released, so it has been taken to this position and it is released. So, one required a disturbing force to start the vibration, then due to as it has reached this maximum position and due to this restoring force, it will be subjected to a restoring force due to this position. So, due to this restoring force it will come back to this original position. So, this is the mean position. So, it can come back to this mean position, and from this mean position, so due to inertia force it will come back or it will go to this side. So, initially we have given some disturbance force, then due to this restoring force it is coming back, it is coming to the mean position, and in this mean position as it is moving, so it is subjected to this inertia force, and due to this inertia force again it will go to upward position and reach the maximum position. So, here again reaching at this maximum position the velocity becomes 0, and again due to restoring force it come back to the mean position, and due to inertia force it goes to the this side. So, we have a disturbing force, we have this restoring force, then inertia force, and if damping is not there, so this motion will continue and we can have a simple harmonic motion. So, when it is at the extreme position, the system has the maximum potential energy, and this potential energy decreases and converted to kinetic energy when it come back to this mean position. So, at the mean position all the energy are converted to kinetic energy and the system has a maximum velocity, and due to this and at this position the system has all the energy as kinetic energy again. So, when it is going to the left side, so this complete kinetic energy again converted to potential energy. So, in some intermediate position, so the energy will be both kinetic and potential energy. So, we must for a vibrating system we must have a means of storing this potential energy, then we must have a means to storing the kinetic energy and a means to by which this energy is lost. So, if the energy is lost, not lost due to damping or due to some other means, so then the system will continue forever and it will vibrate forever, but generally the natural systems, so the vibration stops after some times due to the presence of this damping force. So, the means of storing this energy, so the device, so or the parameter responsible for storing energy is generally known as stiffness of the system. So, that is generally represented by K, and then means of storing this kinetic energy. So, kinetic energy can be stored due to the inertia property of the system. So, that is the mass property of the system, mass will be there, and then this means of energy lost. So, that is another property that is the damping parameter. So, we required mainly these three parameters, that is mass of the system or inertia of the system, then stiffness of the system and damping parameter of the system to represent a vibrating system. So, for a vibrating system we must have a mass, then it must have some stiffness and there must be some damping and a disturbing force F must be acting on the system. So, this disturbing force F may be, it may be periodic, it may be periodic in case of periodic force also. So, the force may be periodic. So, for example, so this is periodic and so this is the force versus time. So, if you plot this force versus time, so this may be periodic or it may be a. So, this periodic response can also be represented by using the sine and cosine term. So, that time it is known as harmonic. So, if the periodic response is represented by using the sine and cosine function, then it is known as harmonic function. So, generally by using the Fourier series, so we can convert any periodic function to its sine and cosine form. So, it may be the forcing may be the initial disturbance or forcing may be periodic or it may not be periodic. Also it may be, you may give a impulse force to the system or the force may be a ramp type or may be the step type. Many different type of force you may apply to the system. You may give a fixed loading to the system. For example, on the bridge a vehicle is standing. So, in that time, so the load is a dead load. So, you are applying a dead load to the system. So, if the vehicle is moving on this thing, so you have a live load. So, the load may be dead or the load may be live, and in the live load, so it may be deterministic or it may be random. So, in case of the deterministic loading, so it may be periodic or it may be this impulse type, ramp type or step type. So, different types of loading conditions are available. So, we will study particularly the harmonically excited system and also we will study the generalized conditions of the systems. So, let us see one more example here. So, you just see this is a spring and damper system. So, the spring and damper, so here we have a single spring and this is damper. So, the vibration you can see here. Similarly, by putting two springs and the damper, so we can see the response. So, the response can be seen here. Okay. So, you can clearly visualize how the motion of a simple pendulum can be represented. So, here we have a spring and this is the mass. So, a pen is attached to the mass. So, as the spring is vibrating, so you can see clearly it is tracing a sinusoidal curve, the motion is sinusoidal. The motion generally becomes sinusoidal. So, in case of the sinusoidal motion, generally we write the acceleration, that is acceleration is proportional to your displacement. If the acceleration is proportional to displacement and takes place in a direction opposite to that of displacement, then that type of motion is known as simple harmonic motion. So, in case of the simple harmonic motion, so you can always write this y double dot equal to minus omega square y, or this y double dot, that is acceleration plus omega square y equal to 0. So, here omega is nothing but the frequency of the response. So, by using a spring and a mass, so you can always generate a simple harmonic motion, but here you are assuming that spring constant to be linear. So, in that case only you can find this type of response. So, if the spring is not linear spring, then the response no longer will be a simple harmonic motion, and that is the study of this course. So, if the spring is not linear, then what is the equation of motion, and if we know the equation of motion, then how to solve that equation motion. So, this is the thing we are going to study in this course. So, similarly, for example, you just take the support in a railway line. So, this railroad you can see, so it is subjected to, so it has different layers. So, you can have the pebble layer, you can have the stones, pebble, and then some this sand layers will be there, and then this railway track will be there. So, the motion of the railway track you can visualize. So, different motion can be represented by different spring and mass, spring and damper system, or it can be written by a Pasternak foundation. So, you can see the response of different layer due to the motion of the train. Okay. So, this basically we can classify the vibration as free vibration or force vibration. If after the disturbing force no force is acting on the system, then the vibration is known as free vibration. So, if a continuous force is acting on the system, then the vibration is known as forced vibration. Similarly, we may have damped or undamped system. So, if damping is there, then we have damped system. If there is no damping, then the system is undamped. Again, this damped system can be divided into three category. So, one will be underdamped, one will be underdamped system, one will be critically damped, and the last one is overdamped system. So, we may have overdamped system. So, we have underdamped system, critically damped system, and overdamped system. Similarly, we can divide the system into a linear system or nonlinear system. So, we will see how we can distinguish between the linear and nonlinear system, particularly the superposition rule can be used to distinguish this linear and nonlinear system. So, we may have a deterministic system and random system. So, generally while deriving the equation of motion of a system, we are using physical coordinate or generalized coordinate system. So, physical coordinate or generalized coordinate can be. So, while solving the or while writing the equation of motion of a system, generally we use different coordinate system. So, one is the physical coordinate system and other one is the generalized coordinate system. So, in case of the physical system, for example, let us take the spring and mass system. So, this is a spring and mass system. So, we can write this equation of motion of the system by using a physical coordinate here at the, we may write the coordinate system, physical coordinate system at the base of the system, or we may take a coordinate system here about the equilibrium position also. So, depending on where we are taking the physical coordinates, so based on that thing we can write the equation motion. The other way of representing the coordinates of a system is the generalized coordinate. So, in case of the generalized coordinates, so we may use minimum number of coordinates to represent the motion of the system. For example, so if we have a 2 degrees of freedom system, so let us take a simple pendulum. So, this is a simple pendulum, the example what we have seen just before. So, in case of the simple pendulum, the position of this mass can be represented by writing the x coordinate and y coordinate, but this x coordinate and y coordinate are related by a constant equation which can be, which is the length of the pendulum. So, we know if the coordinate of this point is 0 0 and the coordinate of this point is x y, then this x square plus y square equal to L square. So, we have one constant equation and two physical coordinates, they are x and y and the constant is L. So, knowing this constant equation and the physical number of physical parameter to represent this equation. So, we can find the number of generalized coordinate. So, the number of generalized coordinates will be number of physical parameter minus the number of constant equation. So, in this case of this simple pendulum, so we have two physical parameter, that is x and y, and also a constant equation, that is L square equal to x square plus y square. So, the number of physical, so number of the generalized coordinate will be only 1. So, that means by using only one parameter, so we can represent the motion of the pendulum. So, here we can use theta to represent the motion of the pendulum. So, or we may write only this x or y to represent the motion of the pendulum, as the other coordinate can be known from the constant equation. So, here if x is known, so we can find y, and if theta is known, we can find x and y. So, by knowing only one parameter, so we can write the equation of motion. So, those are the generalized coordinate system. So, when we will derive the equation of motion, so that time we will know more about the generalized coordinates to derive the equation of motion, particularly when applying this Lagrange principle or Hamilton principle. So, we are going to take the generalized coordinates, and by taking these generalized coordinates easily, so we can derive the equation of motion. So, these are different steps to solve the equation of motion. So, for example, first we must convert a physical system to a simplified mathematical model. So, then we have to determine the equation of motion of the system. Third, we have to solve the equation of motion to obtain the response. Then after getting the response, so we may have to interpret the results for a physical system. So, when we are solving the equation of motion of the system, so we may get, so in this nonlinear system we may get 4 different type of solutions. So, the first type of solution is the fixed point solution. So, first type of solution is the fixed point solution. The second is the second type of solution is the periodic solution. So, if the response is periodic, then this is periodic solution. Then we may get quasi periodic solution, quasi periodic or we may get this chaotic solution. So, we will study regarding all these types of solution in this course. So, let us first see what you mean by the order of a system. For example, let us take this one. So, we have only a spring and a damper. So, a force Ft is applied to this thing. So, we can write this force Ft equal to, so if it displaced by an amount x, then we can write this kx plus cx dot equal to Ft. So, here the equation is a first order equation, but if we are adding a mass to the system, then now we have this inertia force and the equation of motion of the system can be written as mx double dot plus kx plus cx dot equal to Ft. So, this is a first order system and this is a second order system. So, if the spring force is written in terms of kx, then the equation is linear, but instead of writing the spring force as kx, if I will write this equation or this spring force as, let me write this spring force as kx plus k1 x cube, that is a cubic order nonlinearity I have added to this spring, then that equation can be written mx double dot plus kx plus k1 x cube plus cx dot equal to Ft. So, this equation what we have seen, so is no longer linear. So, due to the presence of this term. So, because it will not satisfy the superposition rule. So, what is superposition rule? So, for example, superposition rule have two parts, one is the additive rule and second one is the homogeneity rule. So, in case of the additive rule, so if we are applying a force of F1, so let the displacement is x1. So, when you have applied a force of F1, the displacement is x1, and when you have applied another force F2, the displacement is x2, So, now if we apply this force F1 and F1 plus F2 simultaneously, then if the response is x1 plus x2, then it obeys the additive rule, but if it will not produce x1 plus x2, then the response will not be, or it will not obey the additive rule. So, or it will not obey the superposition rule. For example, now you just apply a force x1. So, the equation will be, in second case the equation will be m x1 double dot plus k x1 plus k1 x1 cube plus c1 x1 dot equal to F1 t. In the second case, let us apply force F2, then the equation will be m1 x2 double dot plus k x2 plus k2 x2 cube plus c x2 dot will be equal to F2 t. So, if we add these two, then we will have, for this F1 plus F2, the equation will be m x1 double dot plus x2 double dot plus k x1 plus x2, but here what we will have. So, in the one case we will get this is k1 x1 cube plus x2 cube, but in actual case this is not equal to k1 x1 plus x2 cube. So, if the response is equal to x1 plus x2, then it must be k1 x1 plus x2 cube, but as this k1 x1 plus x2 cube plus x1 cube is not equal to this. So, it is not satisfying the superposition rule. So, as it is not satisfying the superposition rule, so this equation cannot be a linear equation. So, this is a nonlinear equation. So, in this class you have seen, so how the vibration can be applied to many systems, and also we have seen, so how the superposition rule, we can apply the superposition rule to distinguish a linear and nonlinear system. So, next class we are going to study regarding the linear single degree of freedom system, 2 degrees of freedom system, and the nonlinear systems also. So, okay, thank you.